Okay, so this is our second worksheet on vectors. This one is going to be a little more sort of real world. Well, I'm calling it vector applications here. So let's just do some problems. So the first one here says a cannon is shot at an initial velocity of 50 meters per second at an angle of 25 degrees above the ground. We want to find the vertical and horizontal components of the velocity. So what we've got going on here is we've got some kind of cannon. Well, here's our ground. We're shooting off some projectile with the cannon. This initial angle is 25 degrees here. And so what's going to happen here is that your initial velocity, sort of your v naught, as a vector, what you're going to get is, okay, so the initial velocity is 50, and then we multiply by a unit vector in the direction of sort of this vector here. Well, that unit vector is going to be cosine of 25 degrees, sine of 25 degrees. Here, and I'm going to use a different bracket there. Okay, so what that's going to work out is the 50 now will multiply by through, and we're going to get a vector of 50 cosine 25 degrees, and then 50 sine of 25 degrees. And what's going to happen here is this 50 cosine 25 degrees, that's really the horizontal component of the velocity. The 50 sine 25 degrees, that's going to be the vertical component. So our vertical asked for first. Vertical component is, that's the y coordinate here, that's the 50 sine 25 degrees, and you could work that out to some decimal as well. The horizontal component it's the x coordinate of this vector, that's the 50 cosine 25 degrees. There are our two components here. So when you have a vector, you can sort of decompose it into the vertical part up and the horizontal part down. And really what we're saying here is that if our initial velocity, let's call this one v naught, suppose I should really have a vector symbol over that. What we're going to say here is that there's a vector here, this is our horizontal component, and there's another vector, sort of the vertical component, and let's see, the vertical component, that should be the vector really 0, 50 sine 25 degrees, and then this guy in red is going to be the 50 cosine 25 degrees, comma 0. So if you add the red and the purple together, it gives you, well, the green, the v naught. Okay. Next question. Let's see, you're in a boat that travels at a speed of 6 meters per second. You want to cross a river that is 200 meters wide. Your goal is to reach the other side of the river at a point across from where you started. The river flows at 2 meters per second. So if you maintain a constant direction, what direction should that be? Okay, so let's draw a picture here. So what we've got here's some kind of, well, we'll say this is the river here. So this is our water sitting here. River is here. And the river is flowing, let's say to the right at 2 meters per second. The river flows left to right at 2 meters per second. So we're going to start, I'm going to draw this. Let's suppose we start here. And we're going to swim. Now, what's going to happen here is I want to get to this point right here. So maybe we'll think of this as 0, 0 here. As a point, think of that as the origin. Where we want to get to then, let's see, it's 200 meters across. So this is 0, 200. Now, if you just take off straight for that point, what's going to happen is you're going to move directly toward that point, but the current is going to push you sort of here, and you're going to end up somewhere over here. So what we're going to have to do is we're going to have to aim somewhere up here as our direction. Let's call that V here. So we'll talk about that later. Probably there'll be some kind of angle. Whoops. So we have to aim somewhere there. So as we go out here, the current's going to push us and we'll end up there. So I have some kind of, maybe our actual path. I'm just going to start here and it's going to kind of curve, something like that maybe. We could go and figure out exactly what that is later. It doesn't really matter, but that's the idea of what's going on. Okay, so what we got to think about is as we move along, let's see, our position. So let's say our position at time t. Here. So let's, how about do, I don't know, vector s for position at time t. Well, we're going to start out, well, not really, I guess say it started at 0, 0, but that's not going to add anything, so I don't really need to include that. What I'm going to do is if I've been going for t seconds, I'm going to have two things that get added together. One is t times this vector here. Now, that vector, okay, it's going to come down to, I need some information here. Let's call this angle theta here. So let's figure out what v is, maybe, so we can say this is going to be v. Well, let's just do this. We'll do v, and then we got to figure out what that is in a bit. Plus, so if we're moving with v, and that would be if we just swim with no current, but the current is going to move for every second, if t goes in seconds. That's going to move us at the vector 2, 0. So now we have to figure out what v is. So with v, got this set up here. This is theta. There's v. And we want this to be a vector of magnitude 6 because our speed is 6. So let's find a unit vector in the direction of v. So v is going to be 6 times some unit vector in that direction, which is going to be 6 times, okay, now I have to think about which one's the cosine, which one's the sine. If this is 6, cosine of theta, well, it doesn't matter, if this was 1 here, this direction, cosine of theta would be the vertical part, and the horizontal part would be negative sine theta. So really, this distance would be sine theta, but it's going in the negative x direction. And so our v then should be negative 6 sine theta, comma 6 cosine of theta. We have to figure out what theta is. So what we get in the end is we get sum time t times negative, vector, negative 6 sine theta, comma 6 cosine theta, plus the river current 2, 0. So in the end, we get a vector that is, let's see, t times 2 minus 6 sine theta, and then 6t cos theta. Okay, so there's our t. And really what we're trying to find is theta. Now what we're going to have to use is at this point at the end, this is 0, 200. So what we can say here, well, these t's are just going to keep increasing. We need to find a theta that makes 2 minus 6 sine theta equal to 0. So if the x-coordinate is ever going to be 0, what we need to do is we need to make 2 minus 6 sine theta equals 0. That gives me 2 equals 6 sine theta, which gives me sine theta equals a third. And so this theta is an inverse sine or an arc sine of 1/3 here. Okay, so really the direction here, you could turn this into degrees or something. So in some sense, how do we describe the direction? Direction is whatever sine inverse of 1/3 really to the left. So if you're standing at the river and you go straight across, we're going to go arc sine of 1/3 degrees this way, and that should make this work out. Now, as I'm thinking about this, I think my path is actually wrong here. So what's going to happen here, if you add this together, if you think about it, this is 0 here, that means really my x coordinate is always going to be 0. So instead of this red path here, we can get rid of that, hopefully. There we go. We're going to get a red path. It's actually what you're going to do is go straight like this. But to do that, you're going to aim out here, and the current's going to sort of undo what you do all the time. So I guess my initial picture was wrong. I don't actually curve. I actually start out, and I just kind of keep my bearing there, but I'm actually kind of swimming to my left, and the current keeps continuously sort of pulling me back, so I'm going straight. Okay, next problem. Okay, so this says a swimmer is 50 meters from shore in a river flowing at 2 meters per second. Here, the swimmer swims at 4 meters per second, and the swimmer heads directly toward shore. So part A, there will be a part B later, is how long does it take for the swimmer to reach shore? Right about that here. Let's maybe just look at part B so we get a sense of what's coming up. B is where does the swimmer reach shore? So we'll get both of those answered here. So a very similar picture to what we had on the previous question. Got a river, perhaps the same river, we're going this way. But now I'm going to make my origin here. So my swimmer starts at the origin. I'm not sure the stick figure helps here, but there it is. So it starts there. And the swimmer swims towards shore here. And the swimmer is just going to take off directly swimming towards shore, but that means that going towards shore, whoops, that stray mark there, means going towards shore, I'm not going to head directly there. I'm going to get pushed to the right by the river. So I'm going to end up some point down here. So what we want to think about is that the vector that we move in, so this time I'm going to call v the vector we move in. That's different than v in the previous question, which was done sort of the vector in the direction we're swimming. So now v, what that should really be, well, okay, river's flowing at 2 meters per second. So that's, whoops, 2, 0. 2 in the x, 0 in the y. Plus, as we swim straight towards shore, we're going to get a vector of 0, 4. So we're going 4 meters per second this way. When you add those together, you get 2 plus 0, 0 plus 4. That gives you 2, 4 as your vector that you're heading. So this vector here, well, this is some multiple of 2, 4. So we go, every second, we go 2 meters in the sort of x direction and 4 meters in the y direction. Okay, now if we're 50 meters from shore, we have to make 50 meters of progress. So let's say this is starting at 0, 0. We want to end up here at something, I don't know what, but that's going to have a y component of 50. And so what we're going to see here is, we can write it as a vector, something, comma 50. This equals the amount of time this took us, times the vector 2, 4. So after t seconds, we move t times 2, 4. That's going to equal this. Now, what's going to happen if these two vectors are equal? It means their y components are equal. So we get 50. This is, I can distribute the t. I get 2t, 4t. And so I look at that, that means the 50 has to equal the 4t. And so t is 50 fourths equals 25 halves, or 12.5 seconds. So that's how long it's going to take to reach shore. Now the other question here is, where does the swimmer reach shore? Well, the point that the swimmer reached shore is this, well, question mark 50, but it's the same thing as t times the vector 2, 4. We now know that t is 25 halves. So what I get is this should be 25 halves times the vector 2, 4. This is going to be the vector 25 halves times 2, 25 halves, it's not comma, but times 4. This is the vector 25, 4 divided by 2 is 2, times 2 is 50. So we knew we were supposed to get a 50 here. That's what the 25 halves did. But now we get an x component is 25. So we end up 25 meters downstream. Really is sort of on the shore, but we end up 25 meters downstream. Our swimmer does. Okay. Another question, another swimmer here. So it says a swimmer is 50 meters from shore in a river flowing 2 meters per second. Swimmer is still going at 4 meters per second. Now what happens if the swimmer goes upstream, which is really sort of in my picture to his left, at 10, or upstream in a direction that's 10 degrees. So then we figure out how long does it take for the swimmer to reach the shore. And then B, we want to know where does the swimmer reach the shore. So same setup before, but now basically what's going to change in this picture, instead of going straight up, we're kind of angling to the left and then bringing the current back. So we should end up somewhere over here. We can think about whether this should take us more or less time. But our vector v this time, what that should be, well, we had the 2, 0. The current takes us in this case, x direction, plus, now we're going to get 4, and then a unit vector here that goes 10 degrees upstream. So our setup here, we've got this setup here, I'm going to go this direction, and there's our 10 degrees. And so that unit vector, we did this in problem, I think it was 2, you're going to get negative sine 10 degrees. Sine of 10 degrees is going to be this distance over that, but then it's in the negative direction. And then we'll get cosine 10 degrees in the positive, or in the y direction. And so our sort of vector that we're moving along in is going to end up being 2 minus 4 times sine of 10 degrees, comma, 4 cosine of 10 degrees. Now, same sort of strategy as before, is how long or when do we reach the shore? Is the shore, make sure we get the same question, is 50 meters from where we are. So we're in our y direction, and so we have to set 4 cosine 10 degrees times t. So we move for every t seconds, we move this vector, so t times that vector gives us sort of where we are at time t. We want this to be 50. So our t here, oh no, we're doing this without the vectors this time. It's actually a little bit slicker this way. T should be 50 over 4 cosine 10 degrees. It should be 25 over 2 times cosine 10 degrees. We could write this maybe as 25 halves times 1 over cosine 10 degrees. Now you might be wondering, is that more or less than the previous question's answer? Well, if you look up at this previous question, your time was just 25 half seconds, 12 and a half. Here, we've got the 12 and a half, but we multiply by 1 over cosine of 10 degrees. Now, cosine of 10 degrees is less than 1, so this is going to be bigger than 1, so it's actually going to take us more time. How much more? Well, you could write this out as a decimal. So we can pull up a calculator here. Let's see, so we need to do 25 divided by 2 times cosine of 10. This is going to be in radian mode, so let's say I have to convert this to radians. So I can do 2 pi divided by 360 degrees to give me radians. And I messed that up because I multiplied by the cosine and I was supposed to divide. Here, and so I'm going to get divided by, and I end up with 12.69 here. So this is something like, whoops, maybe 12 point, did I round that right? 69, yes. There. So 12.69 seconds. So something like that. Note it takes a little bit more time. So it was 12.5 before. Okay, then where does the swimmer reach shore? Well, we're going to take our time, which I'm going to now use the exact answer, maybe this form of the exact answer, 25 over 2 cosine 10 degrees. And we're going to multiply that by the x component of the directional vector that we're swimming in. So what we're going to get is 25 over 2 cosine 10 degrees. I'm going to have to multiply that by, it was 2 minus 4 sine 10 degrees. There's a little bit of simplification you could do. I'd probably just plug this in my calculator right now, but there's a factor of 2 I can pull out of each of these. If you do that, you're going to get 25 times 1 minus 2 sine 10 degrees over cosine 10 degrees. I'll give you some kind of answer here. I guess it's an exact answer. I'm going to do an approximate because that seems really kind of ugly. And this is the number of meters downstream we end up. So let's go back and do this. Now I'm going to change my mode, this time to degree. Whoops. There's degree mode. And so let's see, this is my expression. I have to do 25 times the quantity, 1 minus 2 sine 10 degrees, close it up, and I divide by cosine of 10 degrees. Close the cosine, enter. So it's something like 16.57 if I round that meters. So to get something like 16.57 meters, and that's going to be downstream from where we started. We can compare that to the previous answer. Now we were moving off to the left, so this should be not quite as far downstream as before. Previous question, we had 25 meters downstream, so it took us a bit longer, but we didn't end up quite as far downstream. Okay, so that ends our second worksheet here on vectors.